Okay, so I hope I didn't blow your mind with the whole folding process. This should be folded like a zigzag, not like a brochure or burrito or whatever it is that y'all call it. And you should make cuts. The cuts should only go right here, and right here. So these become little doors to open as we go through this. This blank space right here, we're going to use for examples when we are done. So when it's laid out flat on your table, it looks like this. You can lay it out flat while you write on it. That's fine. Just make sure you know how to fold it up. On the other side of the paper, it looks like this, because this is where your glue is going to go. So I was hoping that that might kind of help it make sense how you're going to fold it. Okay? And then if you look over here, triangle proportionality theorem, on the back of this little door, since you've cut right here, is this picture, and then the actual triangle proportionality theorem. So when it's all folded up in your ISN, then you can just open the little door and the stuff goes with it. And then we'll open it up the other way, and your examples will be there. Okay? So we are going to start with the triangle proportionality theorem. And this is going on page 80 in your ISN when we're finished. Okay? So what the triangle proportionality theorem says, open that little door up and we get this right here. Triangle proportionality theorem says if a line is parallel to a side of a triangle, or if a line parallel to a side of a triangle intersects the other two sides, then it divides those sides proportionally. Right? So it has to say if it intersects the other two sides, because I mean I could have a line that's parallel down here that would have nothing to do with that triangle, but this line is parallel and it divides the sides, it divides the triangle proportionally. We've had another line or a segment that goes through a triangle, which was called a mid-segment. And with the mid-segment, E and F would have had to have been the midpoints. So these aren't necessarily the midpoints. They could be, but we don't know that. All we know is that it divides the sides proportionally. Because technically what we have is two similar triangles. So there's two ways to look at this. As similar triangles that are stacked on top of each other, triangle AEF and triangle ABC are similar. We'll talk about why we know that for sure here in just a second. But we can also look at this as a triangle with a line through it. So the only way we've been able to do it up until now is to look at it like two triangles. And we would know that they are similar because if these lines are parallel, then you've got a lot of options here. But if we just look at these two angles right here, those are corresponding angles and they're congruent. They also share angle A right there, which means the little triangle and the big triangle are similar by angle. So if I was concerned with the side lengths here, these two and these two here, then I could just set up proportions with the side lengths. But what this theorem allows you to do is not have to use the whole side, meaning if I set up a proportion, I'd have to put AE over AB when I'm talking about sides of a triangle. But this says it actually divides the sides proportionally, so this makes this super easy because basically your proportion's already set up. It's almost like this is your fraction bar. So this over this equals this over this. And it is that easy. So the length of AE over the length of EB is equal to the length of AF over the length of FC. It's also true that AE over AB equals AF over AC, like whole side over whole side, whole side over whole side. But here we're just looking at this as one triangle, so we have the two pieces of this side equal to two pieces of that side made into a ratio. Okay, so then if I needed something, I could cross multiply and divide. I'd be done with it. All right, so now let's look at the next one. So that was our triangle proportionality theorem. Now we're going to talk about the converse of the triangle proportionality theorem. So that's basically just the opposite. It says, if a line divides the sides of a triangle proportionally, then it is parallel to the third side. So remember, converse is just the opposite. So here, we have this line. We don't know if it's parallel or not, but what we do know is that the pieces are proportional. So since we know that line EF is parallel to line segment BC. Okay, so same information, just remember converse is just the opposite of it. All right, so then the next thing we have is the two transversal proportionality. Now we've had a lot of pictures where we've had more than one transversal, but remember we only look at one transversal at a time. So here it says if three or more parallel lines intersect two transversals, then they divide the transversals proportionally. All this is about proportions. So I've got these lines. They don't actually tell me that they're parallel, but they should in order for this to make sense. So we're going to pretend like we were actually told that they are parallel. So if these three lines are parallel, then I've got all kinds of congruent angles and supplementary angles and stuff in here, but that's not really what we're looking at. We're looking at the lengths of the little segments that get created. So if I just have one transversal and I ignore this one, none of this means anything, because to be proportional, you got to compare two things. But I have these two transversals going through my through my parallel lines. So what this is saying is that these pieces that are here, these two here, it divides them proportionally. You are not guaranteed that anything is congruent, but things are divided proportionally. So AC is the same amount of AE as BD is of BF. And again, your fractions are pretty much set up for you. Like this is your fraction bar. So the length of AC over the length of CE equals the length of BD over the length of DF. So these are very simple relationships. You just have to be careful that you're not assuming anything, of course. Right, so then the last rule we have today is the triangle angle bisector theorem. So we've talked about angle bisectors and segment bisectors and things like this, but when an angle is bisected in a triangle, then some other things happen. Now this looks similar to something I mentioned to you briefly about a week or so ago. Kind of looks similar to the median, but remember that the median of a triangle goes from the vertex to the midpoint of the opposite side. D is not necessarily the midpoint. It could be, but we don't know that. So if it went to the midpoint, it'd be a median, but we don't know if that's the midpoint or not. It doesn't matter because what we're looking at right now is the fact that it bisects this angle. Okay, so an angle bisector of a triangle divides the opposite side into two segments whose lengths are proportional to the lengths of the other two sides. So we get these two lengths. They're not necessarily congruent, but these two are proportional to these lengths. So I'm going to give you what the book and the rule actually says about this, and then we're going to talk about proportions and how you can write them differently and how a different way might help you remember how to set this up a little bit better. But what this is technically saying is that the length of BD over the length of DC is equal to, so these lengths are proportional to these sides, so have to be consistent, left over right, the length of AB over the length of AC. So it's piece over piece equals the whole thing over the whole thing. But with proportions, you can set them up differently and still show the same relationship and still get the same answer in the end when you cross multiply. Because if I'm going to cross multiply, I'm going to multiply BD times AC and AB times DC. There are different ways to write this and still be correct. Basically, if I flipped them both upside down, then I would still end up having an equal relationship and be able to solve and whatnot. Now, another way to write this where I feel like maybe it would make a little bit more sense and stick with you a little bit better. Not really sure why I couldn't have written the rule this way, but if I take this angle bisector, or this angle bisector right here, divides this side into these two pieces. Well, these two pieces are each attached to the other sides of the triangle. So you could write the relationship as the length of AB over the length of BD equals the length of AC over the length of DC. And if you notice that when you cross multiply BD times AC, I'm still doing BD times AC, AB times DC, AB times DC. So I get the same relationship, but here I have the whole side over the piece that's attached to it equals the whole side over the piece that's attached to it, and maybe that would make a little bit more sense on how you set it up. The biggest thing about proportions is, of course, always being consistent. Okay, so we've got the triangle proportionality theorem, the converse of the triangle proportionality theorem, the two transversal proportionality, and the triangle angle bisector theorem. So now we're going to go and look at some examples. So back here, here's our examples. We're going to use this part to work and maybe some of this part here too. And so when we start with this first one, the first thing you want to think about is, how am I really going to set this up? What am I going to use to solve this? And I could use, again, I could just not worry about anything we learned today, and I could say that this triangle here is similar to the big triangle, and I could figure out what this whole side is by adding that and put 32 over the whole side equals 40 over the whole side, and then subtract and do what I need. But this directly applies to the triangle proportionality theorem. Okay, so this is what I'm applying. And what the triangle proportionality theorem says is, if a line is parallel to a side of a triangle, then it divides these proportionally. So remember, this is like your little fraction bar right here. So I can just set that up and put 32 over 24 equals 40 over the x right here. Okay, so then I'm going to cross multiply. And when I cross multiply, that's going to give me 32x equals 40 times 24. Okay, so 40 times 24, it's like doing 4 times 24 and then sticking a 0 on it. Multiplying by 4 is like doubling it and doubling it again. So this is going to give me 32x equals 960, which means x equals 960 divided by 32. Now you may not know whether or not it actually divides evenly, so you could go the long division route. However, when you start getting remainders and stuff, sometimes we don't do the right things with them. You could reduce the fraction a little bit at a time and just get there, in a few steps. But I'm going to give you a second to kind of think about it and figure out what x is all by yourself. Okay, so x equals, this one's really not that bad to do the long division type thought in it, because 32 into 96 is kind of an easy relationship to see. X equals 30. But we're not done. Nobody asked us for x. They asked us, it says find, remember this doesn't just say find DG, I'm not missing the line segment. This reads find the length of line segment DG. So I have to say the length of line segment DG equals 30. So now we're going to look at the next one. It says, are the segments parallel? And the ones that we're talking about here are TU and RS. So if I want to know if something's parallel or not, that is the converse of the triangle proportionality theorem. So this one says if a line divides two sides of a triangle proportionally, then it is parallel to the third side. So I've got to see if it's proportional or not. That's what I have to actually show. I can't just say, oh yeah, they are. But again, I don't have to actually use the whole sides of the big triangle. I'm looking at the pieces, and so my fractions are set up, but my triangle's kind of sideways. So what I would actually set up right here is 67.5 over 54. Then I'm going to put in equals with a question mark, because that's what I want to know. Are these two fractions equal? And then it would be 90 over 72. Because if they are, those two fractions are equal, then the pieces are proportional, which means in turn then the lines are parallel. So a couple of different ways that you could do this. You could reduce both of these fractions and see if they're equal. Like if you could get something that says like, 2/3 equals 2/3 or something like that, then that would be great, and you could show that. But with that having a decimal in it, maybe we don't want to do that. Another way to show it, to see what you want to know, is does this remain balanced and is this equal? You could just cross multiply and see if you get the same number. So if I cross multiply here, it's going to give me 67.5 times 72 equals 90 times 54. Okay. So then when I actually multiply those out, I'm going to get 4860 equals 4860. Now that number itself doesn't really mean anything to me. What I'm really concerned about is, like this was really still a question mark, I didn't know, but at this point they are equal. So since they're equal, that meant that the fractions had the same value to begin with, therefore the sides are proportional, therefore the lines are parallel. So it says, or the segments. It says, are the segments parallel? So we did all this. This isn't my answer, right? I still have to answer the question. So the answer is yes, the sides are divided proportionally. All right, so let's look at the next one. So if I want to solve this next one, this is definitely not the triangle proportionality theorem or the converse of it. It's also not the two transversal proportionality just because it lines up with it. All right? Got to kind of think through this. This one is actually, what it is. It is the triangle angle bisector theorem. Because this is an angle bisector. We're looking for the length of each segment, so I'm going to have to figure out how these pieces are related to each other. So if you remember, what this says is that when the angle bisector divides the opposite side into pieces that are proportional to the other two sides. So the pieces are proportional to the sides. So what it's technically saying is you take the two pieces and make a fraction, so like 6 over y minus 1. And then you take the full sides and make a fraction out of it, but make sure you're consistent. If you're going to put 6 on top here, because it doesn't matter which one you start with, 6 is on top, then the side that's attached to 6 has to be on top over here. This is going to give me 9 over 2y minus 4. Okay. So now I have my proportion. Now I cross multiply, so this is going to give me 6 times 2y minus 4 equals 9 times y minus 1. So this is going to give me 12y minus 24 equals 9y minus 9. So then that means I'm going to get 3y equals 15. So y equals 5. Nobody asked me for y, but I had to find it. So now I've got to go and plug it back in. The length of CD is equal to 5 minus 1. That means that the length of CD equals 4. And then the length of AD equals 2 times 5 minus 4. So that's 10 minus 4. So the length of AD equals 6. Okay, last one. We're going to find the length of each segment. So okay, these numbers didn't actually, I'm the victim of moving things around and squashing them again. All right, so we're going to have to fix this. This side length is supposed to be 9. You can kind of see part of the 9. And this RS is supposed to be 10. We also lost what we're actually looking for. Oh, what happened to my stuff? We're looking for the length, or we're finding the length of line segment ST. Okay, so now let's figure out what we're going to use here. So to find the length of ST, this right here, this triangle here looks much like this picture does right here, which means in order to find this, I'm going to need to use the triangle angle bisector theorem. But the problem is I don't know QR yet, so I've got to find QR. Well, to find QR, I'm going to use this over here, which has 3 parallel lines, 2 transversals. So this is the 2 transversal proportionality. So I've got to use them both. And I've got to use this first. So I'm going to call this X so that I have something to call it. And I'm going to call this y so that I have something to call it. All right, so now I'm going to start with this. The two transversal proportionality theorem says I've got these two transversals, these three parallel lines. So that means that these get cut proportionally. And again, basically my fractions are set up. So that means I'm going to get 4 over 6 equals x over 10. So when I cross multiply, that is going to give me 6x equals 40. So x equals 40 over 6. That does not divide evenly, so that becomes 20 over 3. So x right here is 20 over 3. Not done, because I'm actually looking for y. And so this, when I use the triangle angle bisector theorem, remember the pieces make a fraction. So take the two pieces, and I'm going to get 20 over 3 over 10 equals a fraction of the two sides. Since 20 over 3 was on top, I've got to put the 9 over here. It's going to give me 9 over y. So stop freaking out that you've got a fraction and a fraction. Don't do anything weird with the fraction and a fraction. It doesn't even matter that it is like that, because this is on the numerator, this is the denominator, this is the numerator, this is the denominator. So just like any other proportion, I don't have to do weird things here. I don't even want you to, because I'm afraid you're going to do them wrong right now. You just cross multiply, just like before. So this is going to give me 20 over 3 times y equals 9 times 10 is 90. Now, I've got a fraction. I'm supposed to divide both sides by 20 over 3, right, to get y by itself. That is the same as multiplying by the reciprocal. So when I multiply both sides by 3 over 20, these cancel out. That's why you did it. Okay. You can put this over 1, and you can reduce your fraction sum. You can multiply straight across and then reduce, whatever works for you. I'm just going to go ahead and multiply straight across, and then we'll reduce. So I'm going to get y equals 3 times 90 is 270 over 20. I can cancel out those zeros. So this is just going to give me 27 over 2. That's what I get for y. Got to make sure I actually answer the question. I'm looking for the length of ST. So the length of ST equals 27 over 2. Now, when you glue this in, you put glue on the part that says glue, and then it should fold up into thirds nicely in your ISN for you to have something to refer back to. Get your homework, make good use of your time, help each other, and do your best.